Hello, good morning everyone. I am Srikanth Vellapudi, working as Assistant Professor in the School of Electrical Engineering, VIT Chennai campus. Today I am going to talk about the starters for DC motors. Before going to see what is a starter, first of all we'll see what is the need of a starter for a DC motor. So, when the DC motor is at rest, the speed of the motor is 0, therefore back EMF is 0, and if a DC motor is connected directly to the supply mains, that is suppose 400 volt DC, a heavy current will flow through the armature conductors because from the EMF equation for the armature circuit, armature current is given by the difference of applied voltage and the back EMF divided by the armature resistance, and since armature resistance is very small, the armature current will be very high. For example, consider a 400 volt 20 kilowatt DC motor having a total resistance of 0.5 ohms. If switched directly onto the supply, it would draw a current of 400 divided by 0.5, that is equal to 800 amperes, while the full load current would probably be about 64 amperes. The reason for 800 amperes is because the applied voltage is 400 volts, the back EMF is 0 since the motor is at rest. So the current will be 400 divided by 0.5, which is equal to 800 amperes. The starting current thus is 12.5 times the full load current and would give rise to heating effects and mechanical forces of high values. When running, of course, the applied voltage is opposed by the induced back EMF and therefore a much smaller current flows. A heavy inrush of current at the starting instant may cause that is the effect of high starting currents or heavy sparking at the commutator and even flashovers, damage to the armature winding either by the heat developed in the winding or by the mechanical forces set up by the electromagnetic action. And the third one, the damage to the rotating parts of the motor and load due to the development of large starting torque and fixed acceleration. And the final one is the large dip in the supply voltage. The reason for this large dip in the supply voltage is that because of the very high current, there will be a considerable voltage drop in the connecting wires. So since because of this voltage drop, less voltage will be available across the socket, this makes a large dip in the supply voltage. Hence, for the protection of the motor against the flow of excessive current during starting period, it is necessary that a high resistance must be connected in series with the armature of the motor at the instant of starting and gradually cut in steps as the motor gains speed and develops back EMF, and ultimately when the motor attains its normal speed, the additional resistance from the armature circuit is totally disconnected. If this additional resistance inserted is left in the armature circuit, it would cause additional loss of the energy, resulting in reduced operating efficiency and reduction in operating speed of the motor. However, a very small motor may be started simply by closing the switch which connects it to the supply mains. The reason for it all follows. The resistance and inductance of the armature winding in case of small motors are generally sufficiently large to limit the initial inrush of currents to the values that are not particularly serious. The second one is the inertia of the small armature is generally so low that it comes up to speed very quickly, thereby minimizing the detrimental effects that might otherwise result from the excessive sustained current. Now we're going to see the starters for the DC shunt and compound motors. When we go for seeing the starters for the DC shunt and compound motors, it is very important to know motor starters are generally manufactured in convenient sizes and styles for use as auxiliary with the DC shunt and compound motors. Their primary function is to limit the current in the armature circuit during the starting or accelerating period. They are always rated on the basis of output power and the voltage of the motors with which they are to be employed. The simplest type of starter consists of an additional resistance inserted in series with the armature alone, as shown in the figure. This starter is, however, modified to include few protective devices such as no-volt release, overload release, etc. There are two standard types of motor starters for DC shunt and compound motors: the 3-point type and 4-point type starters. The 4-point starter is employed when wide range of speed by shunt field control is required. When no speed control is required, either type of starter may be used. In this context, it is pertinent to note that while starting DC shunt and compound motors, it is advantageous to keep the field excitation at its maximum value. A large field current, therefore, a higher value of the flux, will result in a low operating speed and in higher motor torque for a particular value of starting current, because motor torque is proportional to the product of flux per pole and armature current. Thus, for a given load current and torque, the motor will accelerate quickly and take less time to reach the lower operating speed from the starting instant. This will result in less heating of the armature during starting. Thus, the rheostat in series with the shunt field winding should be at zero resistance position at the time of starting of the DC shunt and compound motors. Now coming to the 3-point starter. The 3-point starter with its electrical connection and protective devices is as shown in figure. It consists of a series starting resistance divided into several sections and connected to brass studs, brass arc by which the connection to shunt field is made. No-volt release and overload release. This is the overload release. This is a no-volt release. Since only 3 terminals L, F and A, you can see here the 3 terminals L, F and A are available from the starter, it is called a 3-point starter. The last stud of the starting resistance is connected to terminal A. The last stud of the starting resistance is connected to the terminal A, to which one terminal of the armature is connected. The positive supply line is connected to the line terminal. The positive supply line, you can see here, the positive supply line is connected to the line terminal. L from main switch. From line terminal L, supply is connected to the starter arm. From line terminal L, the supply is connected to the starter arm. This is called the starter arm through overload release. This is the overload release. A spiral spring S is placed over the spiral spring. You can see the spiral spring S is placed A spiral spring S is placed over the lever to bring the starter arm back to the off position in case of failure of supply. A soft iron keeper is attached to the starter arm. A soft iron keeper is attached to the starter arm, which is pulled by the holding coil and no volt release coil under normal operating condition. Holding, because there will be a magnetic attraction between these two, so this will be pulled by the holding coil and the no volt release coil under normal running condition. The fair end of the brass arc is connected to the terminal F. You can see here the fair end of the brass is connected to the terminal F here. The terminal F here through the no volt release coil, and to the terminal F, one terminal of the field is connected. The negative supply line is connected directly to the remaining ends of armature and field windings of the DC shunt motor. Coming to the operation of this 3-point starter, when the motor is at rest, the starter arm is in the off position. The starter arm is in the off position when the motor is rest due to action of strong spiral spring. Due to the action of strong spiral spring, the starter arm is at off position due to the action of the strong spiral spring. For starting the motor, the DC supply is switched on by closing the main switch. Keeping starter arm in off position. The starter arm is then turned clockwise. To the first stud and brass arc. As soon as it comes in contact with the first stud, whole of the starting resistance R. As soon as it comes in contact with the first stud, the whole of the starting resistance is connected in series with the armature. The field winding is directly connected across the supply. The field winding, you can see here, as the field winding is directly connected across the supply through the brass arc, and the holding coil is also energized. As the starter arm is turned further, the starting resistance is the starter arm is coming to the stud 2. The starting resistance will be cut off the armature circuit in steps, and finally entire starting resistance R is cut out of the armature circuit. When the starter arm reaches the on position, it is held against the action of spiral spring S by the force of attraction between the holding coil, magnet, and soft iron keeper attached to the starter arm. The starter arm should not be held for an unduly long time in an intermediate position, as it is likely to burn out of starting resistor. This is the operation of the 3-point starter. Now we'll see the function of the no volt release. When the starter arm reaches on position, the resistance is completely cut off and the motor starts running at normal speed. The supply gets interrupted or disconnected. The starting arm will remain in the same position, that is on position, and when the supply is switched on or gets restored, no back EMF will be acting in circuit. The armature being directly across the supply means, and resistance of the armature being low, the motor will draw excessive current and will get damaged. Hence, for the protection of the motor, some device must be provided so that starter arm may reach the off position automatically as soon as the supply is cut off or disconnected or fails, and for this purpose no volt release coil is provided. No volt release coil consists of an electromagnet. Connected in series with the shunt field winding, which holds the arm in on position. Now when the supply fails or gets disconnected, the electromagnet demagnetizes and so releases the starting arm A. which goes back off position due to the spring attached to it and gets disconnected from the supply mains. The other important advantage of connecting the no-volt release in series with the shunt field winding is that it prevents the motor from running away going to an open shunt field, because open circuited shunt field will demagnetize the electromagnet and release the starter arm A, and thus the starter arm will go back to its off position and the supply will be disconnected. Now we'll see the function of the overload release coil. The function of this overload release coil now we're going to see. This coil is provided for the protection of the motor against the flow of excessive current due to overload. We know already that if a motor rated at 10 ampere can carry 125% of the rated current, that is 12.5 amperes it can carry, but if a current of more than that flows through the winding, excessive heat will make the winding burn because of the excessive copper loss. So in order to avoid this one, we'll be using this overload coil. This coil is connected in series with the motor, so carries full load current. When the motor is overloaded, it draws heavy current which also flows through this coil and magnetizes it to such an extent that it pulls its armature upwards and so short circuits the no-load release coil. The no-load release coil, being short circuited, demagnetizes and releases the starting arm, which goes back to off position with the action of spring attached to it, and the motor is automatically disconnected from the supply mains. Thus the motor is disconnected from the supply and is protected against the overloading. The starters for the motors up to 15 kW are provided with overload release to disconnect the motor from the supply mains in the event of an overload. Larger motors are provided with separate automatic circuit breakers. There were some disadvantages of the 3-point starter. We're going to see that before going for the 4-point starter. Now, in 3-point starter, the no-volt release coil is connected in series with the shunt field and the field rheostat, and therefore the current flowing through the field is the same current that flows through the holding coil. Thus, if sufficient resistance is cut in by the field rheostat so that holding coil current is no longer able to create sufficient electromagnetic pull to overcome the spring tension, the starter arm will fall back to the off position. It is this undesirable feature of the 3-point starter that makes it unsuitable for use with speed controlled motors, and that has resulted in the widespread application of 4-point starters. Now we're going to see how this 4-point starter is different from the 3-point starter. A 4-point starter with its internal wiring connected to long shunt compound motor is as shown. It is obvious that when the arm touches stud number 1, line current divides into 3 parts. You can see here, line current divides into 3 parts. One is through this one, other one is through this one, other one is through this one. One part passes through the starting resistance, armature and series field. The second part passes through the shunt field. The third part passes through no volt release. The third part passes through no volt release. The third part passes through the no volt release and protective resistance. Since in this arrangement no volt release coil circuit is independent of shunt field circuit, it will not be affected by the change of the current in the shunt field circuit. It means that the electromagnetic pull exerted by the holding coil will always be sufficient and will prevent the spiral spring from restoring the arm to the off position, no matter how the field restart is adjusted. The possibility of accidentally opening the field circuit is quite remote. Hence, there is greater acceptance of the 4-point starter over the 3-point starter. A motor is started with a 4-terminal starter in the same way as with the 3-terminal starter. Any desired speed above the normal of the motor can be obtained by adjustment of the field rheostat in series with the shunt field. It is necessary to ensure before starting a DC motor that the field circuit is closed. The rheostat in series with the shunt field winding is at zero resistance position, and starting resistance in series with the armature circuit is at maximum value. For stopping the motor, the line switch should always be open rather than throwing back the starting arm. In shunt motors, the line switch can be opened without any appreciable arc, since the motor develops a back EMF nearly equal to applied line voltage and the net voltage across the switch contact is small. The electromagnetic energy stored in the field does not appear at the switch but is discharged gradually through the armature. On the other hand, if the starting arm is thrown back, the field circuit is broken at the last contact button. Owing to the inductive nature of the field, this will cause a hot arc and burn the contacts. So the important precaution we have to remember while stopping the motor is, while stopping the motor, all the resistance in the field rheostat is cut out so that the motor speed falls to its normal value. Then the line switch is opened. This procedure ensures that the next time the motor is started, it will be with a strong field and resultant strong starting torque. So this is about the necessity of the starter and the internal circuitry of 3-point and 4-point starters, and the operation of 3-point and 4-point starters, and about the protection devices we are incorporating in these starters. The reason for going to use the starter in a DC machine is to limit the high starting current. Why the high starting current comes? Because initially we know that the back EMF in a DC motor is the difference between the applied voltage and the back EMF divided by the armature resistance will be equal to the armature current, and the amount of the back EMF induced in a conductor is proportional to the speed of the rotor. Initially, when the rotor is under standstill condition, so the speed of the rotor becomes zero. When the speed of the rotor becomes zero, then the back EMF becomes zero. The back EMF is becomes zero, then the current will be directly equal to the V by R, where the value of the armature resistance of if a motor will be in the terms of 0.5 ohms to maximum 1 ohms, which means the amount of the current will be equal to the applied voltage of 220 volt divided by the resistance, which will be in the order of hundreds of amperes, which is many times more than the rated current of the DC motor. Because if this much current flows through the winding of a DC motor, copper losses will be increased, which causes the heating, which makes the melting of the conductors, which further makes the insulation to damage and the short circuit. So finally, the winding gets damaged, the motor gets damaged. In order to avoid this one, by using the starter, we are trying to increase the amount of the resistance by decreasing the amount of the voltage applied to the motor during the starting. So the amount of the current flowing in the DC motor will reduce, which means the current is within the limits of the rated current of the motor. So once the motor starts rotating, the amount of the resistance introduced by the starter is going on decreasing as we are moving the handle towards the right side. So finally, you can say that as we are moving the starter handle towards the right side, the amount of the resistance added in series with the armature will be going on decreasing. As the speed of the motor increases, the back EMF automatically gets increases, which makes the amount of the current within the limits of the rated current of the DC motor. So we already saw the 3-point starter and the 4-point starter. And the amount of the current that is flowing will be very much high compared to the rated value of the current taken by the DC motor that we saw already.